Very good. Today we're going to talk about constructing a confidence interval. And in this case, we have the case that the standard deviation of population is not given. So this is our goal. Let me change the focus a little bit. Okay, it should be fine. Confidence interval. For the mean, but this is the case that the standard deviation is unknown. Very good. So far we learned that. Let's do the recall as well. Recall that. I'm going to use a different color for the recall. Recall that in previous chapters, we were interested in constructing the confidence interval for the mean, but we had the case that the standard deviation is given to us. It is known. Well, in that case, if you remember, the very first step was to take a sample. We start by taking a sample. From that sample, we find the best point estimate. Then we take the sample mean, or X bar, and we call this the point estimate, which was the most unbiased estimation for the mean. We were trying to build the confidence interval for the mean of the population when the standard deviation was given to us. We started by taking a sample, then we take the sample mean, X bar, which was the point estimate for the population mean. Very well. After finding the point estimate, we identify the confidence level. The confidence level. The confidence level, remember that it was 90%. These are the popular ones. 90%, 95%, 99%, and so on. After finding the confidence level that we denoted by C, we moved and used C to calculate the critical value. So then, by using the confidence level C, we find the critical value. Am I right? The critical value. We denoted those critical values by Z sub C. Z sub C. Okay. In the next step, after finding the critical values, or in this case, we are just taking the positive Z value, which is Z sub C, the critical value, we construct the margin of error. The margin of error. What was the margin of error? Margin of error E equals to ZC times sigma divided by square root of n. So E, or the margin of error, the maximum distance between X bar and the population mean had a formula. E was equal to ZC times sigma divided by square root of N. Well, we used the confidence level to find the critical value, ZC. Sigma is the standard deviation of the population, and N is the sample size. So let us write this down. Sigma is population standard deviation, and N is the sample size. Okay, now that we have E, the margin of error, the confidence interval CI was an open interval, open X bar minus margin of error, comma, X bar plus the margin of error. Am I right? Well, this is my confidence interval. The interpretation was we are 90% confident. We are 95% confident. We are 99% confident that the population mean is between these two numbers. So the conclusion was that the mean mu is within X bar minus the margin of error and X bar plus the margin of error. So this is the case that the standard deviation is given to us, the standard deviation of the population. But in the majority of cases, in real life scenarios, standard deviation is usually unknown. We cannot use the standard deviation sigma. So I expect you to ask, what should we do then? If we cannot use the standard deviation of the population, what is our next step? In this case, if the standard deviation is not given to us, we're going to use a T distribution, And instead of finding ZC, we're going to find the critical value T sub C. So this is the case that we have. Okay. So if sigma is not given to us, we're going to start again taking a sample to construct a confidence interval for the mean of the population, or mu, when sigma or standard deviation is not given. We start by taking a sample as usual. We need the sample no matter what. We take the sample, we find the mean of the sample. Then we find the mean of the sample. What's the mean of the sample? It is denoted by X bar. X bar is the best representative for the population mean, and it is a point estimate. So another name for X bar in this case is the point estimate. Very good. After finding the point estimate, we need to identify C, or the confidence level. Then we need to identify the confidence level, which is C. Again, C, 90%, 95%, these are the popular ones. And if the confidence level is not given to you, you're going to use 95%. Well, what's the next step? In the next step, we need to find the critical value. Now, we need to find the critical value, but it is not ZC. It is going to be T sub C. We are using a T distribution by using T distribution. This is the change that we see constructing the confidence interval for the mean once the standard deviation is not known for us. So what is a T distribution? Let us take a look at our note. Let us take a look at the information about T distribution in the note and go over the definition. Let me open up the note for you. So T distribution describes the variability of the test statistic T, which is equal to X bar minus mean divided by S over square root of N. The sampling distribution of sample means is normal, and a sample standard deviation S is used to estimate population standard deviation sigma. This test statistic is called the T statistic. Like the Z statistic, the T statistic is an estimate. What does it estimate? It estimates how many standard errors the sample mean is from the hypothesized population mean. The T distribution is a family of continuous probability distributions. The width of a T distribution depends on how much a sample standard deviation can vary. The amount of variability in a sample standard deviation depends on how many deviations vary freely when it is computed. So we need the degrees of freedom, which is n minus 1. So the sample standard deviation is computed using the formula below. S is equal to square root of the sum of x minus x bar squared divided by n minus 1. And remember that x minus x bar is deviation from the mean. Well, the degrees of freedom equals to n minus 1. The variability of standard deviations depends on the number of free deviations in the sample standard deviation n minus 1. This quantity is known as the degrees of freedom, or dF. Technically speaking, each degree of freedom defines a uniquely associated T distribution. So for each degrees of freedom, you're going to get a different shape. It is important to know that the fewer the degrees of freedom, the more the sample standard deviation varies. So we are interested in having larger sample sizes. In other words, the smaller the sample size, the more sample standard deviation varies. So the smaller the sample size, the greater the variability in a T distribution, which is not a good thing. T distributions have the following characteristics. T distributions are bell-shaped, they are symmetric, and the mean of the T distribution is 0. Each T distribution depends on the degrees of freedom, df. T distributions have heavier tails and narrower peaks than the standard normal distribution that we saw before. The area under each T distribution is 1 or 100%. As the degrees of freedom increase, the tails are thinner. As the degrees of freedom increase, the T distribution eventually approaches the standard normal distribution. When making inferences about a population mean, the degrees of freedom are equal to the sample size minus 1 or n minus 1. Let's take a look at some T distributions. The curve of T distribution when the degrees of freedom is 1. As you can see, the inner graph is related to the T distribution when the degrees of freedom is 1. It means that the sample size is just 2. When we increase the sample size, the graph becomes more sharper. It becomes much more similar to a normal curve. So remember that you're interested in increasing the sample size. So this is the T distribution that we have. Very well. So before trying an example, let us go back to the board and continue. So you have the confidence level, 90%, 95%, 99%. Now you're going to use T distribution to find the critical value, TC. After finding your critical value, T sub C, we find the margin of error. The margin of error. E, or the margin of error, is now equal to T sub C times S over square root of n. Well, what is S? S is the sample standard deviation, and n is the sample size. Very well. So after finding all of the information that we need, we can move on and construct the confidence interval. Now, the confidence interval is Ci equals to x bar minus E, comma, x bar plus E. Or we say that, hey, we are 90% confident, 95% confident, 99% confident, depending on what is the confidence level, percent. Confident that the mean of the population is in between these two numbers, x bar minus E and x bar plus E. These are the steps that we have to take to construct confidence interval for mean when the standard deviation is not known. Let's go back to the note and take a look at this example. Researchers are very worried about how quickly sea ice is melting. If sea ice continues to melt, it is possible that polar bears will become an endangered species. That means that eventually there may be no more polar bears anywhere in the world. Polar bears use the sea ice for hunting and making their dens. Also, as the ice melts and erodes, there are smaller seal populations. Seals are the polar bear's main source of food. This further endangers the polar bear population. Well, biologists regularly visit Arctic regions to track the health and numbers of polar bears. One important measurement is the weight of adult male polar bears. Biologists estimate that the average weight of an adult male polar bear is approximately 475 kilograms, which is about 1,050 pounds. For the questions below, assume that polar bear weights are normally distributed. So suppose that 4 random samples of 5 polar bears are taken from 4 different areas in Alaska. The weights of the polar bears in kilograms are displayed in the table below. The first sample has 1, 2, 3, 4, 5 numbers in it. The second sample, the same, sample C as well, sample D as well. So what is the degrees of freedom for each sample? So the degrees of freedom is 4. Now we want to find the mean and standard deviation of each sample. We're going to use our calculator to calculate each mean and each standard deviation. We're going to punch these into our calculator and find the mean and standard deviation for each sample. For example, for the first sample, mean is 501.8 with variability with standard deviation 21.55. For the second sample, it is 456.8 with variability 20.89. For the third sample, it is 461.6 with variability 25.32. For the fourth sample, it's 491.6 with variability 14.59. Okay, these are the information in each sample. We are interested in knowing what is the T statistic for each sample. How do we calculate the T statistic for each sample? Let's go back to the board and write it down here. To calculate the T statistic for each sample, we need to follow the formula. The formula is T equals to, well, here we have X bar minus the mean divided by S over square root of, and right, T X bar minus the mean divided by S over square root of N. Okay. So what is T for sample A? What is T for sample B? What is T for sample C? And what is T for sample D? Remember that for each of these samples, we have all the information that we need. For sample A, mean is 51.8 and the standard deviation is 21.55. For the second sample, we calculated the mean, which is equal to 456.8 with standard deviation 20.89. For the third sample, we have mean, which is calculated at 461.6 and S is 25.32, and the mean for the last sample calculated as 491.6 with variability 14.54. Since on the numerator you need the mean of the population, you need to have the mu as well. Is the mu given to us? Remember that biologists estimated that the average weight of an adult male polar bear is approximately 475 kilograms. So we have the mean. Now we need to enter each of these numbers to this formula and calculate T for each one of them separately. So take a look at this. If you want to calculate T for the first sample, T becomes X bar, which is 501.8 minus the mu population mean 475 divided by S 21.55 over square root of n was 5. The sample size was 5. We're going to use our calculator to approximate this number, which gives us about 2.78. This is T sub A. This is the test statistic for the first sample. For the second sample, T sub B is equal to X bar. We calculated the X bar to be 456 minus the mean. The mean of the population is given to us as 475 divided by, well, what is the standard deviation of the sample? Is 20.89 divided by the square root of the sample size, which is 5. This guy is approximately negative 1.95. What about the third sample? T sub C is equal to X bar, which is 461.6 minus the mean of the population, 475, divided by the standard deviation, 25.32, divided by the square root of sample size, which is 5. This number is approximately negative 1.18. And finally, for the last sample, T sub D is equal to X bar, which we calculated as 491.6, minus the mean of the population, 475, divided by the standard deviation, 14.54 over the square root of n, square root of sample size, which is 5. This guy is approximately 2.55. Now I have a question for you. Which of these test statistics shows a mean farther away from the population mean? Which one shows that your sample has the average the farthest from the population mean? Which one would be your answer? Which one has the maximum distance? Is it sample A mean, or sample B mean, sample C mean, or sample D mean? Which one is far away from the population mean? What has the maximum distance? Remember, the mean of the T distribution was 0. Which one is far away from 0? Is it sample A mean, or sample B mean, or sample C mean, or sample D mean? Which one is that? .75, 2.78 has the maximum distance from 0. So your sample A has the mean, which is farther away from the population mean. So you can write, since since T of A is equal to 2.78 is in the farthest position from the 0, so the first sample mean is far away from the population. So that's how we analyze T, calculate the T statistic, and this guy has the maximum distance from the origin. 2.75 on the right hand side is 2.78, and negative 1.95 on the left hand side of 0 has measurement, has distance 1.95, which is less than 2.78. Negative 1.18 on the left hand side of 0, we are just going back to algebra. If you consider this as 0, 2.75 is going to be here. 2.78. I keep telling 2.75. 2.78 is here. Negative 1.95 is here. Negative 1.95. Negative 1.18 is here. Negative 1.18. And you have 2.55, which is just right here. 2.55. So as you can see, for this number, which is associated to the first sample, you have the maximum distance. So this mean is farthest away from the population mean.